time. So some of the questions here say find the eigenvalues. Some of them say find the eigenvalues and eigenvectors. As you have just discovered, eigenvalues, not too bad. Eigenvalues and eigenvectors, finding them all in one shot, it's a fair amount of work, but it's definitely work you want to put time into determining the values of, or at least the process for, because it's pretty important stuff, and it's critical to understand this going into what some of the problems on the previous page, if you still are conscious. All right. So then number 4, find the eigenvalues. All right, so it's same general idea, except we have a cleaner looking matrix here. Cleaner meaning there's more zeros involved. So in theory, that means that things should be a little bit more streamlined. So we're looking at lambda minus 5, 0, 0, 0, lambda 0, 1, 0, lambda minus 3. All right. Now, this is a situation where, well, I'll carry out the process and I'll show you the shortcut through the maze here really quickly in a sec. But let's say I work through row 1. I would say lambda minus 5 multiplied by lambda 0, 0, lambda minus 3. All right. Which corresponds to lambda minus 5. Diagonal down minus diagonal up is going to be lambda times lambda minus 3. All right. The shortcut through the maze here, it's kind of a nice situation. But if you don't pick up on it, you can see that we didn't pay a hefty price for it, because the other two coefficients would have been 0 anyhow. So I didn't have to worry about creating 3 additional matrices. All right. The shortcut is that since this is a lower triangular matrix, it's kind of hard to, well, I'll use a highlighter. All right, it's lower triangular. All you have to do to find the determinant is multiply down the main diagonal. All right? If it were upper triangular, same deal. Any kind of triangular matrix, just multiply down the main diagonal and you'll have the measure of the determinant. All right? If it's a diagonal matrix in and of itself, that's even better. You're still just multiplying down the main diagonal. All right? So bottom line is you could just grab your eigenvalues right out of this, because there's really no work to do. Lambda, poor quality lambda, is equal to 5, 0, and 3. All right. So we found the eigenvalues. All right. But I kind of can't stop myself. We're going to find the eigenvectors that go along with those eigenvalues. All right. So just because while we're here, we might as well. And you know what? I'll even take it as a typo. So, using the characteristic matrix, I'm going to pop in first a 5. So at lambda equals 5. We'd have 0 across the top row, 0, 5, 0, 1, 0, 2, and that would be now this is pretty much already in, it's not quite the echelon form, but it's close enough that you could probably do this one by hand and be pretty satisfied with your answer. Because if you just swap the first and third row and multiply the second row by 1/5, it would be pretty much there. All right, but you could also, there's no need to do it by hand. You could just do it in the calculator. All right, so, but I'm going to set up all the homogeneous equations first. All right, so negative 5, 0, 0, 0, 0, 0, 0, 0, oh, nope, 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 1, 0, negative 3. All right, then the last one, negative 2, 0, 0, 0, 3, 0, 1, 0, 0. All right, so we have each of these eigenvalues, and from those eigenvalues we'll have the corresponding eigenvectors, which would give us the basis for the eigenspace. All right, a lot of eigen this, eigen that, eigen everything. All right, so if you're going to do one of them in the calculator, you might as well do them all, or maybe not. I don't know. I don't want to make that judgment for you. You decide. I mean, because there's also the I don't really know what it's called. It's just I'll call it a testing phenomenon, because it is singular. Things that don't happen every other time you tackle a problem, for some reason happen during a test. Like you don't make a mistake ever, but then the one time you have to do it on a test, all of a sudden you just can't get it right, Like it's just some sort of phenomenon associated with just test taking. It's kind of like the placebo effect, but instead of a placebo, it's a test. Right? It's just is what it is. So, maybe you can do it by hand, but maybe you do it on the calculator just because you're like, I'm not taking a chance on this. What are you, crazy? You could also go the other way. You see, I almost screwed that up. And say, you know what? I never accidentally type things in incorrectly on my calculator except the day I'm taking a test. So maybe I'll type it in the calculator, but I'll also do it by hand if I have a few extra minutes, But just as I predicted, swap the first row and the third row. Wasn't really a prediction. It was just like a statement of what it was going to be. Swap the first and third row and multiply a second row by 1/5 and you have it. So it's really just a matter of rewriting one way or the other. Kind of dealing with that test phenomenon with my son now. For the first time, he's making like dumb mistakes on tests, and he's like, I swear I didn't write that. And I'm like, yeah, you did. You just didn't realize that that's what you were writing. You thought you were writing the right thing, and you wrote the wrong thing. It happens, He's like, there was one moment where he's like, I think the teacher might be changing my answer. And I'm like, your teacher is not changing your answer. I don't think, anyway.
You want the first unit circle with for cosine and sine of the body, I put square root over square root over 2.
Oh, you
so
put that radical.
To make 1, so but I didn't realize.
And like every other time you do it, you never make that mistake, right? Yeah. And you're like, where'd that come from?
It's like some if you cancel square root over square root, it's gonna be 1. So I never realized it.
The one thing about these calculations, it's kind of mindless. So, you're just changing some values as you go along. It's just the more times you have to reproduce something, the more chances there are that there's a mistake in there. So you just got to be really careful. Like copying and pasting. 1, 0. All right, so we just want to make a statement of what our results are really telling us. And this, I find, is where when people make a mistake on this, this is where it tends to happen. Because you really want a shortcut here, but the shortcut can sometimes work against you. So I'll talk about that in a sec. So we know it's going to be x1 plus 2x3 is equal to 0. x2 is equal to 0. And x3 is equal to x3. All right, and that in turn corresponds with a matrix, or I'm sorry, a vector function. X equals x sub 3. We're really just, well, let me not skip it. I was about to skip it and show you where the pitfalls were, but let me not skip it on this one. And then I'll still point out where the pitfalls are. So x1 equals negative 2x3. x2 equals 0. x3 equals x3. All right. So what's really happening here, if you look at what we had in our original matrix and what we have in our solved set of equations here, we're taking the reverse of any signs that are in the last column, the only exception being the last entry, because the last entry is a free variable related to x3. So that is the case where we have a coefficient of 1, right? But what happens is when people start falling in love with shortcuts, they end up making that a coefficient of 0 also. So this should be x equals x sub 3, negative 2, 0, 1. All right, so if you're going to apply a shortcut here, that's fine, as long as you are mindful that that last entry is not really a 0, all right? Because it's x3 equals x3, it corresponds to a coefficient of 1, all right? So for this one, I would say x equals x3 times, it's a safe bet, x1 equals 0. I mean, x1 equals 0, x1 equals 0, all right? Then we have x3 is equal to 0. Actually, this is a weird one. Hold on a sec. I don't even think I could use a shortcut on this one, because we have no solution for x2. So it actually turns out that x2 is the free variable in this one. All right, so I'm actually going to write this one out also. I'm not going to take any chances here. All right, so x1 is equal to 0, x2 is equal to x2, x3 is equal to 0. All right, so that gives us 0, 1, and 0, yeah. X3 is going to be equal to 0 because in this entry here, I just wrote it out of order, but in this entry here, because there's no pivot in the second column, there is no x2 equals, so it must be x2 equals x2, with this one being the x3 that's equal to 0. All right, so this entry, because I wanted to write it in the proper order, but this entry here corresponds to this one. Oh, poor quality. So that last row must have been the case where, so my highlighting is not where it should be. It's just out of habit. Oh, now I'm locked in. Oh, that's rough. Kind of bringing it back. All right, so because x3 is accounted for here, it must be the x2 that's the free variable. All right, so that leads to this one. Maybe that's why this question was only asking for the eigenvalues. All right, but it's still good, right? Because x2 is just referencing a scalar multiplier of the basis vector 0, 1, 0. Right? So we have two bases already accounted for, negative 2, 0, 1, 0, 1, 0. All right, so now the last one is in the proper format, so we could just kind of cut to the chase. So I think I'm just doing a pretty good job of proving that shortcuts are not a good idea for this. So, and staying away from them is probably the best idea. Cutting corners, etc. And so x of 3 is equal to x of 3. And so we have x equals x of 3, 0, 0, 1. All right. So the basis for my eigenspace negative 2, 0, 1, 0, 1, 0, and 0, 0, 1. All right, now depending on what we have to do with that, you know, we could write that as its own matrix. You know, if I needed to find a set of weights that would be a linear combination of these three basis vectors to give me a brand new vector that is in the span of this eigenspace, then I could do that pretty easily. So it's just solving another linear system. So there's a lot of things that we can do with this. It's just basically, if you really think back to the beginning of the course, when I would give you a matrix, it'll like just out of nowhere. It wasn't defined in any capacity as part of like a contextual situation. It wasn't part of a linear system, as in like you had 1x1 plus 2x2 plus 3x3 equals 0. You know, there wasn't anything that came from like finding the intersection between lines in space. It could have been a set of eigenvalues that led to those basis vectors. So when we were trying to determine if a vector was in the span of a given set of vectors, maybe those were eigenvectors, right? So, you know, these aren't too crazy to look at, you know, like when you see them, it's like, they look like any other vector. It's just a question of, you know, what's so special about these? And again, eigenvalues and eigenvectors are vectors that won't get knocked off their span when they're operated upon, right, for a given operation. Right? So if you wanted to transform a vector, these are the ones that are resistant to that transformation. The only way they would differ from their original values is by some scalar lambda. All right. So the next one is pretty much the same concept. Actually, the next two. So I feel like 18 to 20 minutes in, I might be beating us to death a little bit. But so what I'll do is I'll just attach a couple of stars onto these, and we'll save them for another time, because what we're about to learn, something called diagonalization, you guessed it, involves finding eigenvalues and eigenvectors. So we're about to do the same stuff again. So you know, it's not like we're skimping out on the word. It's not, but I'm going to pretend it is. All right. So eigenvalues, eigenvectors of the matrix. Maybe we'll just do one of them, because we're definitely kind of beating this to death a little bit. But it's really more the diagonalization that's important. Maybe I'll save one of these for next week, because you know we're not here on Thursday, so maybe a week goes by and you need a little refresher. I don't know. So same setup. You want the characteristic equation. So first is the characteristic matrix. So down the main diagonal, you're subtracting each entry from lambda, all right, and then from there, you're just negating every other entry. Now in number 4, it was nice because in that case, Yeah, it ended up being lower triangular, so finding the determinant was super easy, barely an inconvenience. So I'm probably going to get sued for that. Lambda minus 5, negative 4, negative 2, negative 4, lambda minus 5, negative 2, negative 2, negative 2, lambda minus 2. All right. So that determinant, or the determinant of that characteristic matrix, should be equal to 0. And so that's what we're going to endeavor to find out. All right, so we'll expand by minors or cofactor expansion. I mean, it's kind of ugly everywhere. So it really doesn't matter which row, or it doesn't seem like it matters which row you go with. So I'll just take the first one so that we don't run the risk of me screwing up the sign distribution. So lambda minus 5. And if we do that, I'm going to use a highlighter here. Still flustered. Here it says lambda minus 5, negative 2, negative 2, lambda minus 2, minus negative 4, so plus 4, negative 4, negative 2, negative 2, lambda minus 2, minus negative 2, so plus 2, negative 4, lambda minus 5, negative 2, negative 2.
Why is it minus 2?
Minus 2?
Yeah,
Oh, no, I'm sorry, I screwed that up.
because it's positive, then negative, then positive, then negative, right?
Yeah, so there should be negative. Thank you. So, diagonal down minus diagonal up in each case. So we have the lambda minus 5 times lambda minus 5, lambda minus 2. Negative 2 times negative 2 is positive 4, so we're subtracting that, so minus 4. Plus 4 times, we're looking at negative 4 lambda plus 8 minus 4. I can clean that up in a minute, although I'm kind of inclined not to. Minus 2 times 8. So minus the product of negative 2 and the other thing, so plus 2 times lambda minus 5.
Shouldn't it be plus 4? Minus 2, minus 2.
Minus 2, where, which one?
We're subtracting 4, right?
Oh, here?
Yeah, exactly.
Again, negative 2 times negative 2 would be 4, but we're subtracting that from, because diagonal down minus,
Positive.
so it becomes negative, because the product becomes positive, but we're subtracting the positive. Because the diagonal up, the diagonal up is positive.
Because it's minus 2 times minus 2.
Right, exactly. Alright. So, whole shibiggity bangity boom here equals 0. And then, pick your favorite method for solving an equation. Yeah. That's where I'm at. So, you can go to the graph, take a quick look-see. Looks like I have 2 unique. And really, for when it comes to the graph, I'm just hoping for nice numbers. And if in absence of that, I'll go to the solver. But in this case, it looks like I have a lambda equals 1 and a lambda equals 10. So I'm going to jot that down. So lambda equals 1. All right. And I'm going to make a little notation here that that's multiplicity of 2. That just means that it's a double root. All right. You can write double root instead if you want. But I just want to make sure I have accounted for all possible lambdas. So lambda equals 10 is the other one. All right. All right. So, and I know to be on the lookout for 3 possibilities because, even though I didn't do it, if I were to distribute this all out, I would have lambda being multiplied by itself 3 times, giving us a power of 3. So I'm on the lookout for 3 x-intercepts. Right? So I found 3 intercepts, just one of them is the double root. All right. Oh, and just to address the pre-calc component of this, that for some reason is often skipped in pre-calc. I don't know why, but I mean I do know why. It's that I know why I skipped it. I can't speak for other people. When I would skip the concept of multiplicity in pre-calc, it was because I hadn't taught the courses that came after pre-calc yet. So I didn't know why it was important to know it. Right? So maybe that's the reason. Maybe it's not. Maybe it's only my reason. But it is a pretty important concept because it helps us determine whether or not we fleshed out all the possibilities. All right? So you could have, let's say, a graph that looks like this, a graph that looks like that, and a graph that looks like that. All right? So if the points around the x-axis form a linear relationship, that's multiplicity of 1, that's a single root. If it appears parabolic around the x-intercept, then that's multiplicity of 2, that's double root. That's what we have here. And if it appears cubic around that x-intercept, that's a triple root, which would be multiplicity of 3. So you could have a single graph that has all those same characteristics just all in one shot. So for example, I'll just do it off on the side here. I could have poor quality. A little bit better. Something like that. All right, so one single polynomial function that has all those characteristics in it. So here I have a multiplicity 2. Here I have multiplicity of 1. Looks like I'm writing mutt. And here it looks cubic. No matter what the direction is, it doesn't really make a difference. This is multiplicity. I'll change that to 1 in a second. Multiplicity of 3 is the last one. I got a little ahead of myself. I was so focused on the fact that I just wrote mutt. But, yeah. All right, so this polynomial would be of degree 6. All right, because I'd have a single root here, a double root there, a triple root there. That's a total of 6 roots. Right? So that means that it corresponds to 6 factors, which means that when you distribute it all out, you would have a power of 6. All right. So why are we talking about it? Well, we want to know what to be on the lookout for when you're solving a problem. I knew that this was going to be cubic, so I was on the lookout for 3 of them. Once I saw that it hit here in a parabolic fashion, I knew, all right, I got 2 of them already. There's my third. I don't have to look any further. All right. That's using the graph to its fullest potential, or a step towards that. Say it again? Good looking graph right there. Nice cubic function. All right, so now we have to find the eigenvectors. Knowing that our eigenvalues are 1 and 10, the unique ones anyway. So lambda equals 1, so we get negative 4, negative 4, negative 4, negative 2, negative 4, negative 4, negative 2 again, negative 2, negative 2, negative 1. All right, we're solving the matrix equation again. It's very easy to lose sight of what you're doing, but you're solving the matrix equation I lambda minus A times x equals 0. All right, we're just doing a wicked shorthand. Wicked shorthand. I don't have my Boston down. It's probably for the best. So negative 6, negative 4, negative 2. I'm going to do a column by column. Just subtracting. Oh, that wasn't it. I looked at the wrong thing. Dagnammit. So that one's going to be 5. Everything else good? Yeah, everything else is fine, I think. Yeah. Got my wires crossed. Alright, so I just have to solve those two bad boys. And the typing commences. 3 by 4. Now we know we're going to get a free variable in here because we have 2 identical rows. It's kind of like last class where we could technically do this one by hand too, but you know, I don't wanna. Look at that. I don't need to math frac that over. 1, 1, 1/2, then a whole lot of zeros. Pick up the pieces in a second, but I'm just going to jot down the solutions. While I'm here, I might as well just double check and make sure I typed it in correctly, because that's a me mistake. And 8. Okay, little RF action going on right now. All right, so we've got a 1, 0, negative 2, 0, 1, negative 2, and a row of all zeros. I'll put this away temporarily. So now we're in good shape because we can come up with our eigenvectors. All right, so again, we're solving for vector x, which represents the eigenvectors. So x1 plus x2 minus 1/2 x3 is equal to 0. All right. So we have 2 free variables. x2 is equal to x2, and x3 is equal to x3. Cross that bridge in a minute. Tackle the other one simultaneously. x1 minus 2x3 equals 0. Bless you. x2 minus 2x3 is equal to 0. And x3 is equal to x3. Oops. All right, so we're going to solve. Isolate the x1. That's really the only one we have to manipulate. All right, so this is going to be the same as saying x1 is equal to negative x2 plus 1/2 x3. x2 I'm going to say is equal to 1x2 plus 0x3. And x3 is going to be equal to 0x2 plus 1x3. All right. Because we have two free variables. Sorry?
Could you slide to the left slightly? Isn't your x3 a positive 1/2?
Wah, 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 wah. Thank you. Oh, now I'm locked out of editing. What can you do? Well, we get the whiteout out. That's what we do. Yeah, there it is. Like it never happened. All right. So that x1 is going to be equal to 2x3. x2 also 2x3. And x3 will be equal to x3. So we could say that x is equal to x3 against 2, 2, 1. I mean, all we're really doing, again, is solving the homogeneous equation. It's just that in the first case, the eigenvector is going to be a linear combination of two free variables. But that, yeah, that's fine. Nothing wrong with that. So x2 just means that when we're developing a scalar, we're just going to have to pick two scalars. All right, but generally, since we let the scalar be equal to 1 anyway, it doesn't make a difference. Okay, so negative 1, 1, 0. Oops, x3, negative 1/2, 0, 1. All right, every eigenvalue will have a single corresponding eigenvector. So it's not the case that you can just say, well, looky here, I have two of them. You know, we're not going to just make up rules on the fly. But what we have been doing, I mean, I guess we could. Maybe that's how new math is invented. People make up rules and then they test them out and see if they work. All right, but what we're doing here is we're determining a scalar or a set of scalars that lead to these being the basis eigenvectors for the corresponding eigenvalues. What we typically do is we let the scalar multiple be equal to 1, because if we're looking for a basis, that seems to make the most sense. All right, so we're going to let x2 and x3 equal 1. We're just stating it a little bit more definitively here. In the past, we would just say, okay, well, here's my eigenvector. Here's, you know, if there was another problem, here's another eigenvector. I'll just take that and make that the basis of my eigenspace. But we have to do the additional step here because the eigenvector really is a sum or the linear combination of these two vectors. All right, so we're looking at negative 1, 1, 0 plus negative 1/2, 0, 1. So the eigenvector is really going to be negative 3/2, 1, 1. All right, and we would do the same thing here. Let x3 equal 1, And so therefore, our eigenvector would be 2, 2, 1. All right, so an additional component here that may be, a little different but the same.